Hi, my name is Eugene, and today I will present about the data extraction section. The first cooler that we have extracted from the PDB project is based on E101. In the first hot stream, the supply temperature of the hot stream is at 393.35 degrees Celsius, and the target temperature to be cooled is at 150 degrees Celsius. Next, the second cooler that we have extracted from the project is cooler E201. The second hot stream supply temperature is at 355.68 degrees Celsius and is cooled to 240 degrees Celsius. The last cooler that has been extracted is E301. In the third hot stream, the supply temperature of the hot stream is at 242.25 degrees Celsius, with the target temperature to be cooled is at 100 degrees Celsius. All the stream data extracted from the plant design project is listed in the table here. Both the CP value and the total heat required are also tabulated here. In our project, there are a total of 3 coolers extracted from the process plant. Moving on, I would like to briefly explain about the minimum temperature estimation that has been done by our group. So basically, the minimum temperature difference is also known as minimum approach temperature, which is the temperature difference needed for heat to transfer. Technically, any value greater than 0 can allow heat transfer to occur. However, when the values are too small, it's usually considered as not feasible. Low temperature differences decreases the need of additional utilities, but it requires increasingly large heat transfer area, meaning that larger heat exchangers are needed. So the trade-off between the operating cost and capital cost should be considered to choose the minimum approach temperature for the network. The optimum choices for minimum approach temperature varies for different types of industries. Since the process involved in our project here is an oil recovery process, so the minimum temperature difference selected for our process here is at 5 degrees Celsius. Based on the assumption of Tmin equals to 5 degrees Celsius, the maximum inlet and outlet temperature of cooling water is calculated and shown in the table here. The maximum cooling water inlet temperature for E1 is 145 degrees Celsius, and the outlet temperature is at 388.35 degrees Celsius. As for E2, the maximum inlet temperature is at 235 degrees Celsius, while the maximum outlet temperature is at 350.68 degrees Celsius. Last but not least, for the E3, the maximum inlet temperature is at 95 degrees Celsius, whereas for the maximum outlet temperature is at 237.25 degrees Celsius.
The water pinch method is used to draw the composite curve of the coolers. First, the inlet and outlet temperature of each cooler is plotted against its heat duty as shown in this TH diagram. From this diagram, we can draw lines between each temperature interval. There are 6 intervals in total of different temperature range. From 95 to 145 degrees Celsius, only E3 is located at this interval, while E1 and E2 are located at the interval between 145 to 235 degrees Celsius, and the rest of streams in different temperature range is summarized in this table. From each interval, the heat duty can be calculated by using the formula Q equals to Cp delta T. For example, E1 and E2 within the interval of 145 to 235 degrees Celsius, the heat duty is calculated by summing up the Cp value of E1 and E2 and multiply with the temperature difference between 235 and 145 degrees Celsius, and we get Q equal to 26,131.68 kilowatt. Then, the heat duty calculated for each interval is added together with the heat duty of the previous interval to get the cumulative heat duty. For example, the Q that we calculated, which is 26,131.68 kilowatt, is added with 5,945.13 kilowatt that obtained from the interval between 95 to 145 degrees Celsius, and we get the cumulative Q equals to 32,076.81 kilowatt. After that, the composite curve is plotted by the temperature against the cumulative heat duty. By drawing a straight line, the pinch temperature is at 350.68 degrees Celsius with a Q pinch of 70,908.27 kilowatt. By using the water pinch method, we can obtain several information, which include the minimum heat capacity, the minimum mass flow rate of cooling water, as well as the temperature of cooling water return. First, the minimum heat capacity can be obtained by dividing the Q pinch with the T pinch, and we get the CP min, which is equal to 214.432 kilowatt per degree C. Besides, the minimum mass flow rate of cooling water is calculated by dividing the CP min with the heat capacity of water, which is 4.18 kilowatt per kg degree C, and we know that at least 184.678 tons per hour of cooling water is required to supply into the cooling water network. Lastly, the temperature of cooling water return can be calculated by the summation of the temperature of cooling water supply and Q total divided by the CP min. Therefore, the temperature of cooling water return will be at 350.8 degrees Celsius.
Hi, my name is Syaza and I'll be presenting the network for below and above pinch. For below pinch, the inlet temperature for cooling water supply is 20 degrees C, while the temperature pinch is 350 degrees C. From the network, the three coolers will be available in the below pinch region according to their temperature target. First, we will calculate the CP for cooler 2 and cooler 3 with this formula. As for cooler 2 and cooler 3, we know the enthalpy was 18,000 kilowatt and 16,000 kilowatt respectively, which will give CP of 56.64 for cooler 2 and 51.15 for cooler 3. For cooler 1, we must find the CP to get the enthalpy of the cooler. First, we must subtract the inlet CP for cooling water supply, which is 214.423, with the CP for cooler 2 and cooler 3 to get the CP for cooler 1, which is 106.64. Then, we will calculate the enthalpy for cooler 1 below pinch, which will be further used in above pinch calculations. For this case, we got 35,000 kilowatt. To get CP pinch, we must use this formula, which will give us 214.43. For above pinch, the inlet temperature of cooling water at pinch is 350 degrees C, while the temperature of cooling water return is 380 degrees C. Only cooler 1 is available for above pinch, thus we must calculate the enthalpy remaining for cooler 1, which is 6,000 kilowatt. Then we calculate the CP for cooler 1, which gives us 214.43. To conclude, the cooling water supply and return is balanced for the network.
Hello, I'm Aina. So, according to the above and below pinch network presented by Syaza previously, we have tried to combine the two to form an overall network. So, for E2, we have targeted the outlet temperature to be 350 degrees C, making our CP required there is 56.64 kilowatt per K. For E3, we have targeted it to be 237 degrees C. So the required CP is 77.85 kilowatt per K. So the remaining CP is 79.94 kilowatt per K. So to supply into E1, we have mixed some of outlet or E2 outlet with E3 outlet and the 79.94 CP, which makes the total CP into E1 is 176.95 kilowatt per K with the temperature of 151.39 degrees C. This makes the outlet of E1 387 degrees C. So this E1 outlet is then combined with the remaining E2 outlet, which makes us get back our CP min total of 214.43 kilowatt per K with the temperature cooling water return of 380.80 degrees C. But then upon checking, we found out that the inlet of E1 exceeds the maximum temperature. So we need to redesign. Okay, now we need to do some modification from our previous network. So for E2 we have remained everything, but for E3 we have increased the CP to become 157 kilowatt per K, which makes the outlet of E3 to become 127 degree C. So to supply into E1, we have taken CP of 13.66 kilowatt per K from the outlet of E2 and mix it with the outlet of E3. So this total CP become 171.45 kilowatt per K with the temperature of 145 degrees C. Upon calculation, it is found out that the outlet of E1 is 388.35 degrees C. So this outlet of E1 is then mixed with the remaining of E2 outlet. So we get back our CP of 214.43 degrees C with the temperature of cooling water return is 380.80 degrees C. So we check again our inlet and outlet temperatures of our coolers. So and everything seems to satisfy the maximum temperatures. So this network is deemed possible and able to reduce our water consumption as well as the water utility cost, which will be further elaborated by Fakhrul Ariffin in the next slides. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Fakhrul Ariffin bin Aminur Rashid. This is the network condition before we integrate an optimum cooling water network where the temperature of the cooling water supply is 20 degrees Celsius and the temperature of cooling water return is 35 degrees Celsius. This parallel network have a mass flow rate of 4042 ton per hour. Next, we move to cost saving. So after we integrate an optimum cooling water network, we managed to reduce the cost. As our plant is located in Sungai Udang, Melaka, we use Melaka Water Tariff from Suruhanjaya Perkhidmatan Air Negara to calculate the cost of water consumption. Based on the water tariff, it consists of 3 bands. Band 1 is from 0 to 50 meter cube, which costs around RM2 per meter cube. The second band is greater than 50 to 100 meter cube, which costs around RM2.05 per meter cube. And band 3 is greater than 100 meter cube, which costs around RM2.50 per meter cube. A few assumptions has been made. The first one is cooling water density is 997 kg per meter cube and the plant operates for 350 days per year. After we integrate an cooling water network, we managed to reduce the mass flow rate from 4042 ton per hour to 184 ton per hour only. So after calculating the cost saving by using the water tariff, the cooling water network without recycle will cost around RM80 million per year, while the cooling water network with a recycle will only cost around RM3 million per year. So by integrating the cooling water network, we managed to reduce cost around RM77 million per year, which translates to 95% of reduction. I think that's all from me. Thank you and have a nice day.